Welcome back. Hope you're doing well. Today we're going to be talking about determinants, which is a scalar associated to square matrices. We've talked a little bit about matrices already as an example of a vector space. This will allow us a way to, by the way, find subspaces of some of these matrix spaces that we're talking about, at least in the world of square matrices. That's stuff we've been talking about in our required videos, but you may have also seen how we can use fields other than the real numbers to define vector spaces, such as the complex numbers. That was our optional video before this one. By the way, a quick note for this one. If you ever get something that kind of interests you in the optional video, I recommend going ahead and checking it out, just seeing what it is. That last video, for example, one for 1.3, was just about 10 minutes long. It's just a nice little foray into seeing something else in mathematics, just to see what kind of is going on behind the scenes sometimes. We are not going to be requiring those videos, meaning we're not going to be seeing those on our homework, although we may reference them here and there throughout the rest of the video, although we'll always try and tie back to the required content. But if you ever see something that catches your eye, this is another way to be celebrating the things that you're learning, is seeing things that really are kind of like, this is something interesting to me. You know, we're always going to be trying to tie into little things like that. But for now, we're going to be talking about determinants, which are scalars assigned to square matrices. In particular, you may have heard things about determinants, about what these things might mean. We're going to be connecting these back to our example from the 1.2 video, AX equals B. If you have A being the coefficient matrix of this matrix equation, and A happens to be a square matrix, meaning you have n equations and n unknowns for your equation. We know that there exists a unique solution whenever you have an invertible matrix here, and that turns out to be an invertible matrix if and only if your determinant is non-zero. So it ends up being important to us to calculate and ask, when is it the case that our determinant is non-zero for a matrix? So we'll talk a little bit about that today in this video. But the question is, how do we even get to talking about these determinants? How do we discuss them? And the notation that we'll use for a matrix of this form, see here that it's just Aij, the same notation that we were using last time for talking about matrices. We'll just call it det A. DET, short for determinant of the matrix A, and we'll write it like this. Notice that this isn't quite the matrix form. We aren't writing the little brackets here. Instead, we're writing these kind of like absolute values, absolute value of A1, A2, AN, and things like this. And that's not necessarily what's being meant here. It's not actually trying to take an absolute value of something like this. This is just the notation that is used for this array of numbers. So the idea behind this is that a determinant of A is not equal to 0 if and only if a system of linear equations with coefficient matrix A has a unique solution. Equivalently, it is not equal to 0 if and only if the matrix A is invertible. This is the thing that we want to use to kind of characterize determinants in today's video. So let's talk about how you might define the determinant in various algebraic ways. Well, let's start with low dimensions. And the reason is low dimensions is we can go through and kind of calculate it. If you have a 1 by 1 matrix like this one right here, determinant of just the number A is itself. So that equation would, for example, have a solution. AX equals B, X is B over A. Well, you can't divide by 0, so as long as your determinant is non-zero, you're good to go. But then you have the 2 by 2s, which ends up being the determinant is kind of like the diagonals going down and to the right, minus the diagonals going down and to the left. So if you take those diagonals, subtract the 2, then that's what you get, AD minus BC. For the three-dimensional one, you may have seen this one already. This is the same sort of thing, except now it gets a little bit more complicated the way that you go through and write this one. You have to do all possible diagonal arrays going through this matrix. And by diagonals here, I mean like you can connect starting from here. Maybe you go from here to here. There's a diagonal, right? And then this diagonal kind of crosses over the boundary. If you think of like the left and the right hand sides being glued, kind of crosses over the boundary here to get to this area right here. And then finally, there is this diagonal going down and to the right. So this is the positive terms in that you have to do to take these determinants. You might notice that this first one, for example, is A11, A22, A33. Those are all the diagonal terms. We get to go through and multiply them together just like this. Then you have A12. That means the first row, second column. That is corresponding to this element right here. And then A23 times A31. We're multiplying each of these together to get this. And then we can continue down this way. But we have 3 more terms to do, and those are going to be the diagonals going down and to the left. These diagonals going from here all the way down to here. So this is what it would look like for a 3 by 3 determinants. Let's maybe do an example before we kind of try and move on here. Let's see it here with this one. Here we have a 3 by 3 determinant to take. We've got a matrix here. We know we are taking a determinant thanks to these little bars over here on the sides. And you can kind of see us go through and add these specific things that we need to add. 3 times 0 times 0, for example, gives us this term. -2 times 1 times -2 gives us this, and then finally 0 times 1 times 3. And then we do the same thing, but going down for the negatives, and that's going to be going for the diagonals going down and to the left as they wrap around our array of numbers here. And that gives us the number -5, which means that if this is the coefficient matrix of some equation, then we can get a unique solution for that. And then we could do the same thing here. Notice that this one's kind of a little bit special. You might notice that this one actually has zeros in very unique spaces. Here, 1, 4, 6, 0, 2, 5, 0, 0, 3. All of the non-zero elements are kind of in a triangle over here on the upper part of this matrix. We would call this one an upper triangular matrix. Upper triangular means that all of the non-zero entries for it are on the diagonal or above it. It's okay, by the way, if some of those are 0 on the diagonal or above it. But we are saying that anything below the diagonal is and has to be 0 in order for it to be an upper triangular matrix. So you might see that there's a unique connection here between what these numbers are and this determinant. Can you spot it? The thing that's happening here is the only diagonal that actually gives you something non-zero when you multiply it all the way through is this one. All the other diagonals, as you kind of go through the way, you're going to get something multiplied times 0 somewhere. So because of that, you see the only non-zero term that we have to go through and add is this one. It's the one of the multiplying through the diagonal. And we'll characterize that in just a little bit. By the way, some of you who have seen taking what are called determinants by minors may have gone through and seen that you can figure out what this 3 by 3 matrix is by noticing that the only diagonals that give you non-zero entries when multiplying this first matrix have to go through the 1 in the third column, or that's the way that you can kind of emphasize that this is where you're actually getting their non-zero elements. If you do that, you can kind of take some sort of what is known as a submatrix of this by deleting all of the elements from that row and column and then multiplying it a specific way. We'll get into more details about that later on, but I just wanted to highlight that in case that was something that jogs your memory. But for now, let's try and use these matrices to try and give us a solution to a system of 2 linear equations. Well, first things first, we've got our system of equations here. We've got a little bit of a coefficient matrix going on. It's just A is A11, A12, A21, and A22 here for this system of equations. X and Y, those together form our solution column vector, X and Y, and then B1 and B2, those form our vector B. So how would I go through and solve this? Well, I might use substitution and elimination before trying to solve using matrices, since we haven't quite gotten to Gauss-Jordan elimination yet. So I might take this first equation and solve it for X. And I can go through and figure out what that is. And then finally, using that X, I can substitute in for the second equation, taking it and plugging it in for here, and then use that to solve for Y. Okay, that's exactly what I'm going to do at this first time. If I do it with all of these kind of general variables, then what I end up getting for Y is something like this. You can check the math yourself, but what's happening here, you might notice here in the denominator, we get something special. Take a look at our coefficient matrix now back at the denominator. You might notice that that's the determinant of that coefficient matrix, right? So the little things that we've already been picking up on already are picking up in this formula. Then we take our Y and we can back substitute. We've already solved for X up here, so we can go ahead and plug that in for Y. That's exactly what we're going to be doing for our back substitution, is plug that in again. And you might notice that after simplifying, the denominator is also the determinant of A, but it's slightly different in the numerator. What's happening in the numerator then? If I go through and calculate what this is in terms of the determinant of a matrix, I'd have to figure out, okay, what goes in the top left and bottom right? I think what would go neatly here is A11 and AB2. You can see here, A11 top left to B2 bottom right. And then I'm going to choose for B1 to be in the top right so that A21 can be in the bottom left. And that's going to get us this formula right here. This one over here on the right. And that gives us what we have for our Y variable. It's kind of like You're dividing by the determinant of the coefficient matrix, but the numerator is the same coefficient matrix. You just replaced the second column with the vector b. So b1, b2 replaces the second column of the coefficient matrix. X, the same thing, except this time b is replacing the first column. Neat little formula there that might help us out in the future there. All right. So in general, though, going through and solving things with determinants is something that does take a little bit of delving into. In fact, there's multiple different ways to do it. And the first way that we're going to give here is an explicit formula for this, meaning we can just go through and calculate based off of the things that are given to us in the matrix. But it's going to be rather complicated, and it's going to take a lot of time to go and calculate things with this. The 2x2 and 3x3 examples are going to be examples of this using this explicit formula. But the reason that they're viable is that they aren't going to be so long when you go through and calculate in this sort of way. So we are going to want to use a couple of different approaches too, one of which is merely axiomatic, one that says, okay, we can say there exists a unique function from the space of matrices to the space of scalars where determinants belong. We know that these are scalars that matrices have. And it has to satisfy certain properties that essentially define it to be the determinant. And we'll talk about what those are in this second approach. And then finally, you may have heard, submatrices may have kind of jog this in your memory here. We can do an inductive process. Remember that the notion of induction is one that says you start from a smaller subcase and then you grow to the subcase that is next to the line. And then hopefully, if you have a base case that works out, you have a line of dominoes for all your subcases that get knocked down by your first subcase. So 1 implies 2, 2 implies 3, 3 implies 4, and that implies it for all sizes. In this case, the sizes are going to be what our n is, and that's what we're running over for our inductive step. So we'll talk a little bit about that inductive approach as well as a way of finding a, say, a 4x4 determinant from 3x3 determinants. But first, let's go ahead and see the explicit definition of the determinant. Here is the formula that we have in general. If you have an n by n matrix, then the way that you define the determinant is that you sum over something called pi n s sub n. Now, S sub n here is going to be the set of all permutations of 1, 2, and all the way up to n. For example, for the set of permutations 1, 2, and 3, the way that you can send a permutation here is something like this. You can send 1 so that it goes over here, 2 that it goes over here, and 3 that it just goes to the same spot. This is an example of a permutation. Now, permutations have a few things associated to them, one of which is called its sign. It's basically asking, the sign of a permutation is asking, how many times are you flipping 2 elements here? How many times are you flipping 2 elements in order to get to your permutation? In this case, all we did was flip 2 elements. So this is just one of something that is known as a transposition composed to make this permutation. One transposition makes this permutation because there is a transposition of one flipping of 2 elements. That's exactly what that means. Now, because that is an odd number of transpositions, we say that the sign of pi is -1. This is -1 if odd number of transpositions. And so this will be for of transpositions. And then if we had something like this instead, let's say we had another transposition where we had to go through and instead send things to 2, 3, 1. The question is, how does this one work? Well, if I look to see how many times I can flip 2 things, it looks like with this one, it's going to take more than one transposition to figure out how to flip this one back around. Well, what I could do is I could start with maybe taking the 1 and 3, for example, down here and flipping these back. If I do that, I have 1, 2, 3, 2, 1, 3. That's after doing one flip. And then I'm back to something that only has one flip instead, right? So that is how we can go through and calculate this. This was one flip of the 3 and the 1 in order to get to this transposition. And now if I flip the 2 and 1 back, now I'm back to just 1, 2, 3. That was 2 transpositions. So that is something that has a sign of +1. And that's if you have an even number of transpositions. So that is the sign of the permutation. But what is the permutation doing at all? What it's doing is it's telling us what the column entry is that we're going to be choosing our column element from. So for example, you remember that we had diagonals going through, and we had like star, 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 and that one was A11, A22, A33. Well, that one belongs to um, the identity permutation, the one that is just 1, 2, 3, right? 1, 2, 3 gets sent to 1, 2, 3. Everything just gets sent to itself. Because what we see here is that in this formula, there we go. In this formula, these are all saying, okay, well, where does 1 get sent to by this permutation? Here, it just gets sent to 1. Where does 2 get sent? It gets sent to 2. Where does the last one get sent? It gets sent to 3. And that's why it's A11. This is pi of 1, this is pi of 2, and this is pi of 3. So this is where those sorts of formulas get to come in. As you can see, a lot is going on in this formula. Indeed, we have to sum this over all possible permutations of the set going from 1 to n. There are n factorial such mappings. So even if we start by the 4 by 4 matrix, we're looking at 4 times 3 times 2 times 1. That's 24 permutations. That means we're summing over 4 possible products, and that's products over 4 different numbers as chosen in a specific way. And then finally multiplied times the sign of the permutation that we're choosing. So this is why we say, okay, well, the stuff that's going on here is possible, but it's a little bit complicated. It's a little bit complicated to go through and check these things out. By the way, if you ever need to go through and calculate a permutation, one thing that you could try and do is say, okay, now let's say that I'm looking at 2, then 3, then 1, right? Let's say we're just taking that bottom row of the things that I'm flipping around. The way that I could start here is I could say, okay, well, how many flips would I have to go through in order to get 1 to go all the way back to its initial position? Well, I could flip the 2 and the 1, or I could just flip the 1 twice, move it all the way over here, right? And that's going to be 2 transpositions. If that ever happens, then I can say, okay, that's 2 transpositions. Then I can see what happens after I move the 1 all the way back. Now I'm just working with 2 and 3, but they're already in the right position. So that one has an even number of transpositions. Now, if I had something like 2, 1, 3, for example, we could see how many transpositions this one would take. This one, I can move the 1 over by 1. I only need to move it over 1. And then once I'm done with that, I'm already back to 1, 2, and 3. So this one has 1 transposition to it. So that's one way that I could go through and do this. You could go through and check now. We've gone through and talked about what our formula was for 3 by 3 determinants out here. You can go through and check that essentially what our formula for the 3 by 3 determinant was is exactly what it should be. Here is that 2, 1, 3 term. Notice that this one has an odd number of transpositions to get it back to its original spot, and that's because this transposition is associated to 2, 1, 3. So that is a way to be using the Sn here to help us figure out what this formula should be. By the way, Sn called the symmetric group. That's why the S is there. It's all the symmetries between the numbers 1 through n that are given here. Now, that's just one way to go through and do it. We can talk about the axiomatic way to define the determinant here as well. Turns out we have a theorem here that we'll need to go through and prove. There exists a unique function. Exists and unique. That means there is one. Unique means there's at most one, because there can't be 2 or more. And existence means not 0. It's got to be exactly 1. There exists a unique function, which is this determinant, which has the following properties. And as we go through here, you may notice that some of these properties are very familiar to us, because these first 3 properties are going to be what are known as the elementary row operations. These are the elementary row operations. Okay. Elementary row operations are the things that we can do to a matrix that do known things to the determinant. If we keep track of what these things are, we can calculate the determinant this way. Here's how it works. The first one, if you interchange 2 rows of a matrix, then the determinant changes its sign. Think of like you're doing a transposition. You're flipping the sign of the determinant, because what you're doing is a transposition of the matrix. You're flipping 2 rows, 2 elements for this matrix here. So that's D1. D2 says if a row of a matrix is multiplied by a scalar R, the determinant is also multiplied by R. So if you multiply a individual row by R, what happens is the whole determinant also gets multiplied by that value. you can kind of go through and check. You might notice that in the formula that we're given for the explicit definition of the determinant, what's happening there is you're multiplying one element from each row whenever you do this sum. Well, if you multiply an entire row by r, then each term gets multiplied by r as well. So that's a way to kind of be convinced of that through the explicit definition. And then finally, D3, if we add a row of a matrix multiplied by a scalar to another row, the determinant remains the same. For example, if I take 1, 2, 3, 4, and if I take this first row, and if I say, for example, take R2, I want to write it like this, and subtract the first row 3 times from it, then I'm going to get a very different matrix. I can keep the first row the same and then take this second row and subtract the first row 3 times. So for example, I can subtract by 1 times 3. That's going to give me a 0 right here. And then I can also subtract by 2 times 3. That's going to give me 6 to subtract from, and that'll give me a -2 here. So this is something that will not change the determinant of my matrix. These two have the exact same determinant, and you can go through and check that if you would like. All of these are known as the elementary row operations. If these are some things that you would like to see a refresher on, I recommend going and checking out chapter 3 of Ricardo's textbook, which has some of the elementary row operations and some other things about what matrices are able to do in that text. Let me know if you have any questions during office hour as well. D4 is this one that essentially says you can't just take the determinant of I to be some number, whatever you want. I here is the identity matrix. We know this in 2 by 2 to just be the ones with ones on the diagonal and zeros elsewhere, but you can extend this to any n by n using the same property. We ask for the determinant of the identity matrix to just be 1. This is something that we are asking of the formula. We could technically ask it to be 2 if we wanted it to be, but that would ruin some things that we like about the determinant. So we ask for the identity's determinant to be 1. If you have all these 4 properties, you've got a unique function. There's one that exists, and it is unique. Before going through this, let's talk about some of the corollaries with this theorem. So let's suppose, for example, you have a square matrix and that you get that B is obtained from A by applying elementary row operations, D1 through D3. Then the determinant of A is 0 if and only if determinant of B is also 0. Let's see why. Well, what happens if, for example, you get that B is obtained from A applying elementary row operations? So B ends up having a determinant of 0. Maybe we get it to be an upper triangular matrix, and it's easy to determine that, something along those lines. So if we know the determinant of B is 0, well, what does doing elementary row operations do to the determinant? Does it ever make it 0 out of its own right? No. Determinant 1 only changes its sign. If something's non-zero, it's going to stay non-zero. Multiplying by a scalar r, well, we're not trying to multiply any of our rows by something times 0. That's not going to work for us. So we are always going to get something non-zero from applying D2. And then finally, D3, doing this operation makes the determinant remain the same. So with these 3 row operations, we're never changing something away from 0 if it is 0. And if we get something that is non-zero, indeed, that means our determinant was non-zero to begin with. So this is our if and only if way of clarifying this. Then corollary 2 says that the determinant of B equals 0 whenever the matrix B has a 0 row. Okay, well, this is something that we can go back to the explicit definition and be convinced of, since we know that every entry or every term in our sum from our explicit definition has a 1 element from each row in that sum. And so because of that, if it has a 0 row, every term has a 0 as a factor. So it's going to be 0 all the way through. But we can also use our theorem, a neat little way to show this corollary. The proof idea, if you will, for this determinant is to multiply the 0 row by the 0 scalar. And that's just applying D2. Well, you're going to get the exact same matrix, and hence you're going to keep having 0 there. Then there's corollary 3. Determinant A equals 0 if and only if the matrix A is non-invertible. Well, let's talk about how we reduce row echelon form. Again, something we talk about in chapter 3 of this text and is assumed more or less for this course. Let's let B be the reduced row echelon form for the matrix A. Well, if A is invertible, then we know that we can go through this square matrix and reduce row echelon to get our matrix to be B equals I. Well, I is certainly not invertible, excuse me, I is certainly invertible. It is its own inverse, and hence we can go back and invert A in the same way. So we can talk about it being invertible because essentially saying that it has a determinant that is non-zero. That was our principal idea back on the first slide. Otherwise, well, B is going to have a zero row. B, if it's in reduced row echelon form, if it's ever not in the identity form, then it has a zero row, because this is how the row echelon forms for these square matrices work. Here, this is not reduced row echelon, this is just row echelon form. But you can see what we mean here when we say zero row, something like this. What is going on here in this picture, by the way, is that you have all of these things called pivot columns, which are all determined by any place where you have a pivot elements like this. Here, this would be an example of a pivot column because it has a pivot element somewhere in it. That pivot element, when row echelon form, is going to be a 1. That is the first one in its row, right? Everything else has to be a 0 to the left of it. And everything below it is also going to be 0. So you can see here that you have something like this going on. This one over here is also a pivot. There's zeros just going to the left and downward from it, but everything above it, it can be anything. The stars allow us to say, okay, that can be any number, at least in row echelon form. But you can see here that some of the columns here are not pivot columns. For example, the one circled in red. This one is not a pivot column. And that's because there is no pivot here. The star just says it can be anything, even if that star ends up being a 1 or a 0. Whatever that ends up being, this is not a pivot column. It is not the first one in its row and the last one in its column, or the last non-zero element in its column. So that's what we have going on with the row echelon form, kind of just to remind us about what it means to have a 0 row there. If you have a 0 row, then we're back to corollary 2, and our determinant is indeed 0. So, by the way, this argument tells us that the properties D1 to D4 are enough to compute any single determinant. How can we do that? We can start with, okay, let's see if we can do reduced row echelon form. We can start from a determinant of 1. If we know the row operations that get us from A to B, right, from B being the identity matrix, a determinant of 1, if we keep in track what those row operations are, we know that, say, the first operation, maybe it multiplied the determinant by R. Then, if we ever need to get from this matrix determinant back to the determinant of the first matrix, we just divide by R instead. We're just reversing the steps that we're taking. We can reverse the steps in order to figure out what the determinant of our original matrix was from the matrix at the very end. That's the idea behind this remark. Just saying real quick here that these are examples of things where determinant of A is non-zero. That's where everything is a pivot column. That is an invertible matrix versus a one with a 0 row in it, which we know will have a determinant of 0. Other things that are interesting about determinants, if you have something with 2 identical rows inside of it, then you can subtract one row from the other. Right? Remember that we say that that does not change the determinant of this matrix. So I can say that this matrix here with 2 identical rows is the same as taking this one and subtracting this matrix, this row from the third row, first row from the third row. Yeah, that's the order. Subtracting the first row from the third row. If we do that, we just get zeros there, and we have our 0 row, and that means that we have a determinant of 0. If a matrix A has 2 proportional rows, then that's the same sort of thing. We're using the same elementary row operation, but this time we're multiplying times R. Remember that if we have 2 proportional rows, then I can either A, think of this as R times the original row without that R being multiplied times the scalar. That's using D2. Or I can think of it as going back and subtracting R copies of the first row from the third row. That is D3. However I'd like to think of it, that is going to give me eventually, as I simplify it, a matrix with a 0 row, and I'm going to be back to 0 for that determinant. Finally, if the rows of A are linearly dependent, the determinant of A is 0, as in this case, A cannot be invertible. Remember that linearly dependent means it has a linear combination of those rows that equals 0. Right? And those that instructions of this relationship between each of these rows tells us that there is a way to basically add and subtract each of the rows from each other so that eventually you either get to two proportional rows or two identical rows so that you can just subtract one from the other and get to 0. So that is a way that we can be looking through and talking about determinants here. Other neat things about determinants, just to be able to calculate them neatly through matrices before we go on to our last way of calculating determinants, is that square matrices are diagonal whenever you have a matrix that is only going to be non-zero on the diagonal. So for example, the identity matrix is a diagonal matrix, but so is this one, 1, 0, 0, 2. This is also a diagonal matrix. Anything along the diagonal is fine. The thing that is wrong and what makes something not a diagonal matrix is having something like this, where you have a non-zero element in the off diagonal. So this is not a diagonal matrix, whereas the identity matrix is one. The matrix is upper triangular on the other hand, if all the entries below the main diagonal are 0. You can see that that happens when its row number exceeds its column number. So those would need to be 0. So 1, 1, 1, like this, 1, 1, 0, 1, this matrix would be a upper triangular matrix. And we know that we can find its determinant very neatly. The determinant for either of these matrices is just the product of the numbers down the diagonal. Neat little thing there that helps us speed things along whenever we have nice forms for our determinant. And it also tells us, by the way, as an aside, that if we want to determine the determinant of something, then we only need to get it into row echelon form. A matrix only needs to be in row echelon form, because then, just like we had a couple slides ago, we're back into that triangle form. So if we ever get it in that form, then we're good to go. Here's another way of thinking about it. Essentially, if we are adding rows to one another for working with matrices, we can break apart matrices into, if we have everything here in a row, is a sum of corresponding entries here in maybe one entry versus another, and we want to figure out the relationship between these two determinants, then what we can do is just say, okay, if everything else is the same in the other two rows, so everything else is equal, and we're just splitting apart based off of this first row, then the determinant of this matrix Z is the same as the determinant of X plus the determinant of Y. A couple ways to see this one, maybe. One way is to go back to that explicit form and think about it in terms of you're taking each element from the rows and you're splitting it apart into two terms. One term belongs to the matrix X, the other term belongs to the matrix Y. You're using the distributive term to break apart things along the A1 plus A1 prime angle. And then the same thing for A2, A2 prime, A3, A3 prime, whenever these pop up in your formula. You know that you'll always have exactly one of these in each of those terms, and that each one will break apart into two, one for X and one for Y. So you should get the entire formula from the explicit definition there. All right, but this is also kind of a neat way of thinking about how we can connect these matrices together. By the way, with the property D2, the one about scaling rows with each other, this means that the determinant depends linearly on each row of a matrix. Linearly, because why? Because you can do scalar multiplication with it. That will allow you to multiply times R. And then you can say, okay, well, then the determinant also works neatly with how you add rows together. What that means is that if you have the determinant of, on each row of a matrix, for example, if you have determinant of, let's say it's something like this. Let's say that we have row vectors, X and Y here. So let's say we have Rx plus SY, and then we just have dummy rows down here. We'll call them, I don't know, Z1, Z2, something like this. And whenever I have a determinant like this, then I can split this apart linearly, something like this. R times the determinant of X, Z1, Z2, plus S times the determinant of Y, Z1, Z2. That one won't write. Here we go. So I can essentially split this one apart, just like with the linear operators I was doing before. Scalar multiplication, it works neatly with that, and so does addition. So the reason that we talk about this additive law for rows is to establish that the determinant is something called a linear operator. And this is something that we will focus on later on in this course, is what are linear operators? What are some neat things that go neatly with them? In particular, this one is a linear operator on the rows of each matrix. And here we can say, as long as everything else is equal, we can be working neatly with this on each row. So we're establishing the determinant as one of these examples. Then there's the last way to go through and define the determinant, and that is using submatrices. Let's say, for example, I have this 3 by 4 matrix like I have up here in this picture. And let's say that I take it to delete some rows and columns for my own leisure. Let's say I delete the first and the third rows and the second column. What I'm left with is another matrix if I compile it all together, but it's got 1 fewer column and it's got 2 fewer rows. So I've taken a 3 by 4 and gotten a 2 by 2 submatrix out of it. What we did was we just erased the first 2 rows, or we erased 2 of the columns and 1 of the row in order to get there. So we get to specify specific rows to make and then delete all of the other columns. Now we're going to be working with square matrices, and we're going to want our submatrices to be square as well. So we're going to require, for at least this stuff, that our columns and rows each be the same number for our submatrices. So let's start by saying we have a matrix of rank m, meaning we have an m by m matrix that essentially, when you get it into its row echelon form, right, we can say that its determinant is non-zero. So that is a rank m matrix. In fact, we could even say that the size of A is bigger than m, but that whenever we consider the number of pivots inside of A, that it has m non-pivot elements. Then we'll say that, then our theorem says that if A admits a k by k submatrix with non-zero determinant, by the way, if and only if k is less than or equal to m, and in specific greater than 0. So this is a way for us to work to make submatrices that give us non-zero determinant. And this is a neat way to kind of be building up ways of figuring out determinants and things like this, as we'll see using some induction. What we do is we say, okay, take an n by n matrix, and let Mij denote the n-1 by n-1 submatrix that deletes the ith and jth row of A. So here we are specifying an I and a j that we are about to delete. This Mij now has 1 fewer row and 1 fewer column. It is an n-1 by n-1 submatrix. So here's the theorem. For any k and m inside of 1 going to n, then whenever I take this determinant, I can do an expansion of it by the kth row. And what that's going to mean is that I'm going to consider each of the following things. Let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9 as my matrix. Then I'm going to take the determinant of, let's say, for example, j is something that I'm summing over going from 1 to n. But I'm going to go ahead and specify a row. I'll specify the first one. And I'm going to take the determinant in the following way. I'm going to start by noting what this element is. It's going to be 1 times. And now I'm going to take this column and this row, and I'm going to delete them out. And then I'm going to take this determinant, 5, 6, 8, and 9. And that's going to be my way to start taking this determinant. Then I do this again. But this time, I'm fixing the row, but I'm moving forward on the column that I'm trying to delete. So I denote this column real quick. I have 2 times, and I delete that column in that row. I have another matrix to take. That's going to be 4, 6, 7, and 9. Now, I'm actually going to end up subtracting here. You can see here that there is a notation about how I'm actually going to put plus and minus on each of these things. And it's going to be the sum of the column and row number that I'm choosing. For example, here I am on column 2 and row 1. 2 plus 1 is 3. -1 to the third power is -1. So I'm going to be subtracting this one. And then finally, I'm going to continue expanding on this first row since I haven't gone through each of the row elements here. And I'm going to note the first element of this third column, and then I'm going to delete first row, third column. And that will give me another matrix to take. And I can go through and calculate what this is. So that is expansion by the kth row. We can also expand by the mth column instead. Essentially, we're doing the same process, but instead of taking every element on a row and moving to the right, we're taking every element on a column starting from the top and moving down, switching our -1 +1 along the way. So these are those formulas there. Now, real quickly, we can get signs for those row and column expansions like this. Start with a plus in the top left, and then you know that if you ever move and right or down from that plus, you're switching your sign. So for example, everything along this diagonal is going to be plus because anytime that I need to move onto the diagonal, I have to move right then down, then right then down. That's an even number of steps to get from the top left corner. So all of those are going to be plus. These are also going to be plus, like for example, this third row first column element is signified with a plus whenever I make its expansion because that is still 2 steps away from the first row first column. Unlike this one, this is the minus sign because it's on the second row first column. It's only 1 step away from the plus. By the way, you may have this question, and your intuition may be right. The significance behind these pluses and minuses has to do with the sign of a permutation. Has to do with the sign of a permutation that we are taking. So it's pretty interesting stuff kind of going on there. There's a lot of connections behind each of these definitions. So these are what is meant behind the -1 to the power of part. So that kind of explains this, times the element in the thing that we are multiplying times the determinant of the submatrix that we are making. Let's go ahead and see that example here with this same matrix of what we have. If we expand on the first row, what we are doing is we are deleting first row, first column, and writing the determinant like this. 1 times this remaining matrix, 5, 6, 8, 9, minus 2 times this remaining matrix, and then plus 3 times this remaining matrix. The plus, minus, plus all come from that matrix of signs that we had on the previous slide. If I go through and multiply that out, I can get 0. So that's how that works, expanding by the first row, but I didn't have to expand by the first row. I could have expanded by anything. I could have expanded by the second column. Notice the way that this one works. I'm going to start on the top middle entry because that's the first element in my second column. That's exactly what we have in this matrix here. And I'm going to delete everything in that row and column to get another submatrix, this one 4, 6, 7, 9. Notice that I'm multiplying times -2 here because in our matrix of signs, this one is associated with a minus. So I have this element to be going through and taking. Then I can go ahead and isolate each of the other entries in the second column, getting submatrices along the way. And that's going to give me another thing to calculate. And what do you know? I get the exact same determinant this way, the determinant of 0. So this is a way that we can go through and calculate things using expansion. This is an inductive way of determining determinants. Another way to go through and do this is to find this determinant, for example, is to just apply the, what was it called? The axiomatic definition of the matrix. Let's subtract the first row from the second row and from the third row, and let's see what we get. If we do that, then we get 1, 2, 3, subtract from 4, 5, 6, just gives us the row 3, 3, 3. And then that same one being subtracted from 7, 8, 9 gives us triple sixes down there on the third row. And because of that, we see that we have 2 proportional rows on these bottom 2 rows. And we know with any matrix with 2 proportional rows gives us a determinant of 0. A couple of the determinants of properties of determinants that are going to be very useful for us moving forward. If we have 2 square matrices and we multiply them together, the determinant of the product is the product of the determinants. You may have seen this one before. If you have 2 n by n matrices and you flip their product, remember that flipping the order of A and B does not give you the same matrix B times A. That is a very different matrix oftentimes, but the determinant ends up being exactly the same. If you have an invertible matrix, the determinant of A inverse equals the determinant of A to the -1. We can determine this because we know the determinant of I is 1, but we also know that the determinant of any matrix times its inverse, which is the identity, is going to be 1 as well. That's because A times A inverse is the identity matrix. These 2 things are the same. Well, we just saw that the determinant of the product is the product of the determinants. So the determinant of A times the determinant of A inverse equals 1. And that, when we divide by the determinant of A, gives us this formula. So that is a way that we can go through and prove that. And then finally, if we have a scalar multiple for our matrix, notice that the determinant does not scale linearly if we multiply the entire matrix by a scalar r. In fact, it multiplies by r to the n, where n is the number of rows. You may know why this works, because what we've done is we multiplied the entire matrix by r, which means we've multiplied each row by r. Well, we know that the determinant scales linearly with multiplying each row by r, and we've done that n times, n being the number of rows. So that's where we get this Rn formula from. Now, determinant of the transpose. One last thing here is that the determinant of a transpose gives us that whenever you take the determinant of something like this, where again, here you see all the columns and rows have been flipped. That is what the transpose does. It turns out that that is the exact same determinant as before. Essentially, the proof behind that is that we know that expanding on a row versus expanding on a column gives us the exact same formula. And so you can see here that there's the column and the row that are the exact same thing, and the expansions are going to be identical as well. As a consequence, anything that we talked about with rows for a matrix, we can do the same thing with columns for a matrix. For example, if one column of a matrix is multiplied by a scalar, the determinant is multiplied by that scalar as well. Interchanging two columns of a matrix just changes the sign of its determinant based off of a transposition. And then if a matrix A has two proportional columns, then the determinant of A is 0. And then finally, adding a scalar multiple of one column to another does not change the determinant of the matrix. So some neat little properties to kind of be playing around with here. We have a lot of information about how to be working with determinants, how to find determinants, and neat ways to be able to play around with determinants. We've done 3 different definitions today for the determinant, each one useful in its own specific context. These properties, however, are ubiquitously useful. We'll use them anytime that we need to be discussing the determinant. But that does it for us today. Thank you so much. Have a wonderful day.